One problem with Q-learning is that it takes many experience tuples to converge. This is expensive in terms of interacting with the world because you have to take a real step, in other words, execute a trade, in order to gather information. To address this problem, Rich Sutton invented Dyna. Dyna works by building models of T, the transition matrix, and R, the reward matrix. Then, after each real interaction with the world, we hallucinate many additional interactions, usually a few hundred, that are used then to update the Q table.
DynaQ is an algorithm developed by Rich Sutton intended to speed up learning or model convergence for Q-learning. Remember that Q-learning is model-free, meaning that it does not rely on T or R. T being our transition matrix and R being our reward function. It doesn't know it. Q-learning does not know T or R. Dyna ends up becoming a blend of model-free and model-based methods. Here's how it works. So let's first consider plain old Q-learning. Dyna is really an addition to Q-learning. So let's start with the regular Q-learning and then look at how we add Dyna into it. So we initialize our Q table and then we begin iterating. We observe S, we execute action A, and then we observe our new state S prime and our reward R. We then update our Q table with this experience tuple and repeat. And we do that over and over and over again, interacting with the world, and our Q table becomes better and better. So when we augment Q-learning with DynaQ, we add three new components. The first is that we add some logic that enables us to learn models of T and R. Then, for lack of a better term, we hallucinate an experience. So rather than interacting with the real world like we do up here with the Q-learning part, and this is expensive by the way, we hallucinate these experiences, update our Q table, and repeat this many times, maybe hundreds of times. This operation is very cheap compared to interacting with the real world. So we can leverage the experience we gain here from an interaction with the real world, but then update our model more completely before we step out and interact with the real world again. After we've iterated enough times down here, maybe 100, maybe 200 times, then we return back up here and resume our interaction with the real world. The key thing here is that for each experience with the real world, we have maybe 100 or 200 updates of our model here. Let's look at each of these components in a little more detail now. So in this part where we update our model, what we really want to do is find new values for T and R. The point where we update our model includes the following. We want to update T, so I'm calling it T prime for the moment, which represents our transition matrix, and we want to update our reward function. Now, remember that T is the probability that if we're in state S and we take action A, we'll end up in S prime. And R is our expected reward if we're in state S and we take action A. I'm going to show you in a moment how we'll update T and R. Here's how we hallucinate an experience. First, we randomly select an S. Second, we randomly select an A, so our state and action are chosen totally at random. Then we infer our new state, S prime, by looking at T. And we infer our reward, our immediate reward, R, by looking at big R, our R table. So now we've got S, A, S prime, and R, or a complete experience tuple, and we can update our Q table using that. So the Q table update is our final step, and this is really all there is to DynaQ. We've added these three sections, and what's missing, and I'll get to in just a moment, is how do we update our model of T and our model of R. So what I'm about to show you are my methods for doing these things. They may not correspond exactly to what Rich Sutton did, so keep that in mind. But I've used these methods in practice and found them to work really well. Let's start with learning T. Remember, T of S prime represents the probability that if we are in state S, take action A, we will end up in state S prime. To learn a model of T, we're just going to observe how these transitions occur. So, in other words, we'll have an experience with the real world, we'll get back an S prime, and we'll just count how many times did it happen. So I'm going to introduce a new table I call T count, or TC, and it goes like this. So we initialize all of our T count values to be a very, very small number. The reason for that is later on you'll see that if we don't do that, we could get in a situation where we have a divide by 0. Then we begin executing Q-learning, and each time we interact with the real world, we observe S, A, and S prime, and then we just increment that location in our T count matrix. So every time we see a transition from S to S prime with action A, boom, we add a 1. And that's pretty simple. That's it. Okay, assume now we've been watching our interactions with the real world for a while, and we would like to consult our model of T. I would like for you to write an expression for T in terms of TC, or T count. Okay, so fill in this text box with your opinion of how we can compute T of S prime in terms of T sub C. And remember, T sub C is just the number of times each one of these has occurred. Okay, consider that state S and A are somewhat fixed. What we're trying to find is, given S and A, what's the probability of a particular S prime? So we'll begin this by just consulting how many times did this transition occur. In other words, how many times when we were in state S, did action A, did we end up in S prime? So that's how many times this particular transition occurred. Now we just need to divide it by the total number of times we were in state S and did action A. So essentially it's the sum over I, where we have I iterate over all the possible states of T, S, A, I. So this is the number of times in total that we were in state S and executed action A. And so this ratio ends up being the probability that we'll end up in S prime if we're in state S and take action A. The last step here is, how do we learn a model for R? Now remember, when we execute an action A in state S, we get an immediate reward, little r. So again, big R, SA, is our expected reward if we're in state S and we execute action A. Little r is our immediate reward when we experience this in the real world. So big R is our model, little r is what we get in an experience tuple. So we want to update this model every time we have a real experience. And it's a simple equation, very much like the Q-table update equation. What we have is 1 minus alpha, where alpha is our learning rate. And again, that can typically be something like 0.2. Anyways, we multiply that times our current value for R. And then we add in, of course, our new estimate of what that value ought to be. And we just use R for that new estimate. So it's alpha times little r, which is our immediate reward, or our new best estimate of what the value should be, plus what the value was before times 1 minus alpha. So we're weighting, presumably, our old value more than our new value, so we converge more slowly. But that's it. That's a simple way to build a model of R from observations of interactions with the real world. Before we close, let's recap really quick how DynaQ works. So we start with straight regular Q-learning here, and then we add 3 new components. The three components are: we update models of T and R, then we hallucinate an experience and update our Q table. Now we may repeat this many times, in fact maybe hundreds of times, until we're happy. Usually it's 100 or 200 here. Once we've completed those, we then return back up to the top and continue our interaction with the real world. The reason DynaQ is useful is that these experiences with the real world are potentially very expensive, and these hallucinations can be very cheap. And when we iterate doing many of them, we update our Q table much more quickly.